In this video, we're going to take a look at NTP Stratum values and see exactly how they work in practice. First, we'll explain what stratum actually means. Then we'll demonstrate how stratum values change in a real network when synchronisation is lost. And finally, we'll discuss why stratum is so important in NTP installations. For today's demonstration, we're using 2 Stratum 1 GPS servers, 3 Linux industrial PCs, a network switch, and a Windows 11 PC. These devices are operating at various stratum levels, which we'll explain as we go through the video. We've put links to all this equipment in the description box below. Let's start by looking at what NTP Stratum actually means. Stratum is a fundamental concept in the network time protocol that represents the distance from a reference clock. Think of it as layers in a timing hierarchy, where each layer represents how many hops away a device is from the ultimate time source. The stratum value is transmitted as part of the NTP packet data itself. Every NTP packet contains a stratum field that tells receiving devices exactly how many hops away the sender is from a reference clock. This allows NTP clients to automatically evaluate and compare different time sources based on their stratum values. As a side note here, the stratum field is just one of many pieces of information contained within each NTP packet, including timestamps, precision indicators, and synchronization status flags. If you're interested in learning more about the complete structure and contents of NTP packets, we've done a comprehensive video covering all the packet fields and their functions. You'll find the link in the description box below. Stratum 0 devices are the reference clocks themselves, things like atomic clocks, GPS receivers, or radio time signal receivers. These aren't actually NTP devices. They're the physical time sources that NTP servers connect to. Stratum 1 devices are NTP servers that are directly connected to Stratum 0 reference clocks. These are considered primary time servers and provide the most accurate NTP time. In our setup, our GPS NTP servers are Stratum 1 devices because they're directly connected to GPS receivers. Stratum 2 devices are NTP servers or clients that synchronise to Stratum 1 servers. They're one step removed from the primary time source. If a Stratum 2 device is providing time to other devices, those other devices become Stratum 3 and so on. The stratum value can go up to 15, with Stratum 16 being a special case that indicates the device is unsynchronized or unreachable. Any stratum value of 16 or higher means the time source shouldn't be trusted. You might temporarily see Stratum 16 during system setup, whilst NTP is still acquiring its initial synchronization, or during reconfiguration when sources are being changed. To put this in real-world context, Stratum 1 servers are typically found in data centres, universities, and research institutions that need the most accurate time. Stratum 2 servers are common in corporate environments and internet NTP pool servers, with most office workstations and network equipment usually operating at Stratum 3 or 4, which is perfectly adequate for most business applications. This hierarchy system serves 3 critical purposes. It helps NTP clients choose the best time sources by preferring lower stratum values. It prevents timing loops where devices might end up synchronising to each other in a circular fashion, and it improves network efficiency. Right, now let's see NTP Stratum in action with our test network. Our demonstration NTP test network includes 2 Stratum 1 NTP servers and 3 industrial Linux PCs. For our demonstration today, the Linux PCs are running the Crony NTP software. We've arranged the devices into 2 separate NTP distribution networks, each with its own Stratum 1 GPS server. These GPS servers are both locked to GPS satellites and provide the most accurate NTP time reference available. Just to add some clarification here, when I talk about 2 different NTP networks here, I'm talking about how the time is distributed across the different devices. All of these devices are connected to the same physical Ethernet network. The first NTP distribution network is our main system. It consists of a Stratum 1 GPS server feeding time to the first industrial PC, which becomes Stratum 2. This first PC then provides time to a second PC, making it Stratum 3. So we have a simple hierarchy. GPS server at Stratum 1, first PC at Stratum 2, and second PC at Stratum 3. The second NTP distribution network is our backup system. It has its own Stratum 1 GPS server, feeding time to a third PC, which becomes Stratum 2. Here's the key part. We're using the second system as a backup for the Stratum 2 server in the first system. The first PC is configured to synchronise to both its own GPS server as the primary source and to the third PC from the backup system as its secondary source. This gives us redundancy. If the main GPS server fails, the first PC can fall back to getting time from the backup system. To complete the overview of our hardware setup, we've also got a Windows 11 mini PC out of shot that we're using to access the Linux systems remotely to provide the screen capture that you can see displayed on screen now. We've set the system up to show the Stratum value of each Linux PC with the value automatically updated periodically. All of these devices are connected via a network switch. Okay, so the system is running and our Stratum 1 servers are both synchronised. Let's start by looking at the current state of our network. First, our Linux PC from the main system. As you can see from the live display, it's synchronised to our main GPS server and showing Stratum 2. The second Linux PC, also part of our main system, is synchronised to the first Linux PC and is showing Stratum 3. Our third Linux PC, which is our secondary system, is synchronised to the backup GPS server and is showing as Stratum 2. So our normal hierarchy is working perfectly. Both GPS servers at Stratum 1, our main system with the first PC at Stratum 2 and second at Stratum 3, and our secondary system at Stratum 2. Now here's where it gets interesting. I'm going to disconnect the GPS antenna from the main GPS server. This will simulate a failure of the primary time source. Since the first Linux PC is configured with both the main GPS server and the third PC as its sources, let's see what happens to our Stratum values as it fails over. Right, I've disconnected the GPS antenna from the main GPS server. There's an important point to mention here. You won't see the Stratum change to 16 immediately. This particular GPS NTP server has an upgraded oscillator that puts it into holdover mode when it loses GPS lock. In holdover mode, it continues operating normally for a period of time using its internal oscillator. As a side note here, this particular server can actually continue operating in holdover mode for quite some time. But for this demonstration, we've set the programmable holdover timeout to be as short as possible. Holdover operation is a very interesting and complex topic. If it'd be of interest, maybe we could do a video on this. Let me know in the comments below if this is something that you'd like to see. Okay, I'll pause the recording here while we wait for the server to flag a synchronisation error and move to Stratum 16. Now that we've waited for the holdover period to expire, let's see what's happened. The main GPS server has lost GPS lock and the holdover period has elapsed, so its Stratum value has moved to Stratum 16, which means it's unsynchronised and shouldn't be trusted as a time source. The first Linux PC, which was synchronising to the main GPS server, has now automatically failed over to the third Linux PC as its backup source. Since the third Linux PC is Stratum 2, our first PC has now become Stratum 3. The second Linux PC, which synchronises to the first PC, has now moved to Stratum 4, since it's one hop further away from the time source. The third Linux PC remains at Stratum 2 since it's still synchronised to the backup GPS server, which continues to have GPS lock. This demonstrates the beauty of the NTP Stratum system and proper redundancy configuration. When the primary time source failed, the network automatically recalculated the hierarchy. The first PC seamlessly failed over to its backup source, maintaining synchronisation whilst the Stratum values adjusted to reflect the new path to the reference clock. If I were to reconnect the GPS antenna to the main server, you'd see the Stratum values gradually return to their original configuration as the devices detect the primary time sources available again and fail back to the preferred lower Stratum source. So why is this Stratum system so crucial? There are three main reasons: hierarchy maintenance, loop prevention, and network efficiency. First, the Stratum system maintains a clear hierarchy and network timing. Lower Stratum values normally indicate more accurate time sources, so NTP clients can make intelligent decisions about which servers to trust. A client presented with both a Stratum 2 and Stratum 4 server will naturally prefer the Stratum 2 source because it's closer to the reference clock and likely to be more accurate. But the second reason is perhaps even more important. Stratum values prevent timing loops. Without this system, you could end up with a situation where server A synchronises to server B synchronises to server C, and server C synchronises back to server A. This would create a circular reference with no connection to an actual time source. The Stratum system prevents this by ensuring that time always flows downward through the hierarchy. A Stratum 2 server will never synchronise to a Stratum 3 or higher server. If an NTP server can only find higher Stratum sources, it will declare itself unsynchronised rather than create a loop. This is why you'll sometimes see devices show Stratum 16. They're effectively saying, I can't find a suitable time source that maintains the proper hierarchy, so I won't provide time to anyone else. It's a safety mechanism that keeps the entire NTP network stable and prevents timing chaos. The third crucial benefit is network efficiency and load distribution. By creating this hierarchical structure, Stratum helps distribute the load across the network and reduces the burden on the most critical Stratum 1 servers. Instead of having thousands of devices all trying to synchronise directly to a limited number of Stratum 1 servers, the hierarchy allows Stratum 2 and 3 servers to handle much of the client load. This not only reduces network traffic and server load at the top levels, but also improves overall network efficiency by keeping time synchronisation traffic more localised. A well-designed Stratum hierarchy means that most devices can get excellent time accuracy without overwhelming the primary reference sources. The combination of these three functions, quality indication, loop prevention, and efficient load distribution, makes the Stratum system absolutely essential for any reliable NTP deployment, whether you're running a small office network or a large enterprise infrastructure. Speaking of deployments, there are some important configuration best practices worth mentioning. Always configure multiple NTP sources, ideally at least 3 or 4, so your systems can continue operating even if 1 or 2 sources fail. When possible, prefer lower Stratum sources, as they're generally more accurate. But don't ignore geographical proximity and network path quality. A nearby Stratum 3 server might actually provide better time than a distant Stratum 1 server due to network delays. It's also worth clearing up a common misconception about Stratum values. Many people assume that a lower Stratum number always means better accuracy, but this isn't necessarily true. The Stratum value tells you the distance from a reference clock, not the actual accuracy. A well-maintained Stratum 2 server with excellent network connectivity might be far more accurate than a poorly configured Stratum 1 server with network issues. In this video, we've explored NTP Stratum values and seen how they create a hierarchy that ensures reliable time distribution across networks. We've demonstrated how Stratum values automatically adjust when time sources fail, showing both the failover process and the importance of proper backup source configuration. We've also discussed why this system is crucial for maintaining network timing integrity and preventing dangerous timing loops. I'd love to hear about your own NTP setups in the comments below. What stratum levels do you typically see in your networks? Are you using GPS servers, internet pool servers, or a mix of both? And let me know what challenges you've faced with NTP synchronisation. Understanding stratum values is fundamental to working with NTP, but there's another critical field in NTP packets that works alongside stratum to help clients make timing decisions. If you'd like to learn about how NTP indicates whether time has been properly set and warns of upcoming leap seconds, you might like to watch our video on the NTP leap indicator. The link is on the screen just here.